So I've been doing this a few years, and when I get to the planets, sometimes it's like, it's stuff you've grown up with as like a kid, you know these things, you're like, oh my gosh. So I try to make it interesting, and I'll try to kind of tell you what's, what's important. Well, actually, it won't be as much facts, but it will be a little bit of science, obviously, since this is a science class. Okay. So we talked earlier, and you already kind of had a sense for these rocky planets, these 4 rocky planets: Mercury, Venus, Earth, and Mars. Okay. Notice I threw one more up here. Actually, Earth's moon. It's a player. It's spherical. Remember, things actually can become spherical if they have a certain amount of mass. So these are surface shots of these objects, these planets and the moon. I say they're surface shots, but I'll try to explain this as we get there. But one of the characteristics of Venus, tricky little Venus, is that actually it's very cloudy. It's basically got chronic cloud cover, Venus is. Venus's clouds are made, though, not of liquid water droplets, but liquid H2SO4, liquid sulfuric acid. Like, dude, really? So anyway, so it's hard to really get a surface picture of Venus. The closest we've come, and there's a figure in your textbook I'm going to show you, or a photo in your textbook, the closest we've come to seeing the surface of Venus is like, gosh, was it the mid-70s, when the Soviet Union landed a probe on Venus. Pretty harsh, though, because it didn't transmit for very long, but actually we do have surface pictures of Venus just from that. If you're like me, I'm like, well, why didn't we ever go back? I don't know. I scratch my head sometimes.
So surely we have better technology nowadays.
Yeah. I guess there's no, it's got to be something in it for the old mighty dollar. But we need to kind of talk about how these surfaces are as they are. I agree. So there are no dinosaurs at the center of the Earth. I don't mean to disappoint you. I like to dream. I like to watch movies, silly movies. But we do have a sense for what's going on in the interior of the Earth for a number of reasons. One is seismology. Basically, anytime there's an event like an earthquake, or it could be a man-made event, basically picture somebody like a drill or something like that. Actually, that energy goes through the matter of the Earth, okay, the Earth's material. And depending upon what that characteristics of the matter is, that energy will carry differently, okay? So basically, with all of the planets, we kind of compare the planets to Earth. Makes sense, okay? So the Earth, we can kind of think of the layers of the interior of the Earth. The gray thing is the Earth's core, like the movie The Core. Anybody in here seen the movie The Core? And we'll admit it, okay? So the core, it's not on my slide, and I don't know if your author emphasizes it, but actually the core is not, it looks solid, doesn't it? And it is very heavy, rich in, of course, Fe is iron. Our core is very rich in iron. There is that color didn't show up very good, okay? There actually is an inner solid core, so I'll put S for solid, and there is an outer liquid core. I haven't drawn these to the right. Okay, but basically there's a solid orb rotating in a liquid, kind of like an amniotic fluid sort of thing. So that's the core. Outside the core, we have the mantle. And if you're like me, I think of mantle, I think of kind of liquid mantle. But you know what? Actually, as it turns out, all of this is mantle. Here we have the solid mantle, and here we have liquid mantle. I'll put an L for liquid. So it's just kind of a small thing, but it's true. The whole thing is mantle. Then we have the crust, and the crust here is kind of tan. So that's the crust. It's solid, obviously. Okay, so that's kind of how our Earth is broken down. So we know generally what the other objects have with regard to their gray, represented gray here, their core, their mantle, and their crust. And so here's how it goes. And these are listed actually from largest, the Earth, to smallest, the Moon. . So you might be like, well, if we've only been on Venus just barely once, right, the Soviet Union, then how do we know what we know about Earth? And like this says, there's various ways. One is by studying the density, basically a ratio of how big it is to how much it weighs. That kind of gives us an indication how much dense material or light material you have. Another thing we're going to talk about is this protective cocoon that the Earth has, something called a magnetic field. Okay, if they have a magnetic field, that means that actually they are somewhat ooey gooey in the center. No magnetic field, not so much. Okay, so planets generally, especially early on, were really warm. Planets were really warm. The Earth was so warm that, as you might imagine, the Earth's surface was liquid. Okay, the rock was liquid. Why were the planets warm? They were warm the same reason, basically, like you told me on your test, the fact that something small, gravitational potential energy, was converted to thermal energy. The other reason that planets are warm actually has to do with something. Remember, we said you can carbon date. Hi. You can carbon date. You can radiometrically date rocks to know how old our solar system is. Okay. So that decay process, radioactive decay, actually releases energy. And so that's something, this decay process is still going on to release energy in the interior of all these planets. So that's two reasons to add thermal energy. So there's this, not always, but a lot of times when I'm looking for a vocabulary word, I will pull out this word planetary differentiation. I think in your textbook, they liken it to, let's see, Italian salad dressing. Okay, Italian salad dressing. So it works like this, that with Italian salad dressing, you have your water, you have your water and your oil, okay? And if you mix it up, okay, if you let it set, then the more dense water is going to settle and your oil is going to float. That's just the density thing. So kind of like that, and it's a gravity thing. Why does it do that? Well, because gravity is pulling the more dense liquid down. So actually, the same thing happens with the planets. So the center of the planets actually have the most dense material, and the crust is the least dense material. So planetary differentiation. So planets have basically been cooling off ever since the sun turned on some 4.5 billion years ago. And just like you probably know, a large object actually will cool more slowly. And so actually, you saw a minute ago, kind of ranging from size, the Earth to the Moon's the smallest. Okay, so the Earth actually is the warmest. Well, and it's taking longer to cool down. So I mentioned geological activity. When I say ooey gooey, I'm talking about geological activity. Geological activity requires that it's warm enough for that rock still to have molten rock somewhere. And actually, a minute ago when I said the mantle, we have a solid part of the mantle and a liquid part of the mantle. Okay? So, are these objects geologically active? Drum roll. Okay. So here we are, we see the same list, and like I said, it's listed from largest to smallest up here, okay? So in terms of if the large things cool down more slowly and the small things cool down more quickly, you can kind of already get a sense for, do you have any sort of liquid in their interior, okay? So as it turns out, these two objects, the smallest, of course that would be the Moon and Mercury, geologically dead. Dead. Okay? Which just means that they have no liquid in their centers. When we talk about geological activity here on Earth, that's plate tectonics, but that's like the volcanoes and the earthquakes, the plates moving. They aren't doing that. Okay, Earth and Venus, geologically active. So again, why? Because they're cooling down more slowly. come visit them in another 4.6 billion years and see if they've cooled down to the point of no longer having any sort of fluid in their interior. But I guess I should mention another 4.6 billion years from now, and that's about when the sun is going to turn into a red giant. So that's going to be problematic. All right, so Mars, the jury's out. But I hear Mars was in the news today, that NASA's got more evidence that, or caught water flowing on the planet Mars, which is pretty darn exciting. Go over here. Over here. Okay. So, if you pick, I didn't bring silly putty. One of these days I'm going to have to invest in silly putty. But just like this girl up here is kind of working with silly putty, okay, you know that if you're careful, you can take silly putty and, wish I had some right now, you can like mold it and, okay. But if you go ahead and take silly putty and apply your forces quickly, just like down here, she looks kind of disappointed. She has broken her silly putty, okay? So actually something that's solid, like silly putty is clearly a solid. It's kind of got elastic properties, but it's definitely not a liquid. But solids actually, in the form of planets, can shape and deform over time, okay, if your force is applied gradually. If that same force is applied quickly, you have that sort of issue. Okay, so planets cooling off. Actually, anything cooling off, you have 3 different ways that you can get energy from point A to point B. And in this case of a planet, basically we're taking energy that's in the interior and we're trying to get it out. Okay? So the 3 different ways you can transfer energy. There is convection. And convection, you might have heard the term kind of convection cells before. But convection is being shown here by this. Basically, I'm going to say hot, don't touch. Hot in the center or the core of the planets. Okay, so one of the things we know about hot fluids, okay, is that they will rise. Just like hot air rises in your house. Okay, so it will rise and it will cool off. It rises because it's less dense, by the way. And it cools off and it becomes more dense. And then it will sink, okay? And then it will heat up and it will rise, okay? So this actually, that process takes, MY stands for million years. So it takes 100 million years to go up, because it's buoyant, less dense, it rises, it cools, it becomes more dense, it sinks, it heats up, it rises, it cools. Okay? So that's a lot. So convection is one way to move heat outwards for the planets where they're concerned. Conduction is the next way. And I guess my A's and B's are gone here. But conduction, B should be right here. Okay, so conduction is kind of what I call the butt to butt to butt to butt sort of thing. Conduction is basically what happens if you are heating a pan of water, and let's just say you put a metal spoon in your pan, and after a while, I don't know how much of a while, but you come back and you try to pick up your metal spoon, and it's hot. Okay, it hasn't come in contact with your oven. Okay, basically what's happened is that thermal energy has, via molecule to molecule to molecule, moved up your spoon. Okay, and so here we're showing it actually in, I didn't emphasize, the lithosphere, is the crust in the upper part of the mantle. So within the lithosphere, okay, actually it's transferred that way. And then the last one, C here, is radiation. So there's that little squiggle mark there, that is C. So let's see. Radiation, it's kind of cool. We've talked a lot about the cousins of energy. Okay, so one thing about all forms of radiation is they travel very fast, the speed of light in a vacuum. Okay, so I just think it is so cool that this energy, and so if we're talking thermal energy, we're talking infrared, right? That this energy would take off in all directions going the speed of light. When it, down here, it took 100 million years to work its way up, and then it's like, out of here. I just think that is so cool. The contrast. Okay, so one of the ways we can infer or understand what's going on in the interior of planets is to study to see if it has a magnetic field. Only planets that have are somewhat ooey gooey can have a magnetic field. So on Earth, you can actually create a magnetic field. Now this reminds me of those where you could like draw facial hair on a face, like you can give them eyebrows and a mustache and a beard. Okay, these are like metal filings there. So this is just a little bar magnet and showing you that the pink lines are the invisible magnet field associated with every bar magnet. Every bar magnet will have a magnetic north and magnetic south pole. Over here actually showing you that you can create a magnetic field. So these pink lines are a magnetic field. You can create it. This is like a copper top battery right here. So basically all you got to do is get electrons moving through the battery in a circle. One way to do that is basically take a copper wire that can carry your electrons or your charge, wrap it around something, and then as electrons go, okay, that basically right there in that kind of gray block right there, that neutral gray block, is around that electrons are going in a circle, okay, and it creates this magnetic field. So those pink lines are the magnetic field that's been forced or created. Well, what does this have to do with the planets? Well, the planets can actually do the same thing as this right here. We're making charges move around, okay? What planets do basically is if you have fluid, if there's some ooey gooiness in the interior of your planet, you can have charged particles, which would just be like the iron, charged particles. With I'm doing my finger like that, we all know planets rotate on their axis of rotation. It's that planet rotating on its axis and having liquid, okay, in its core that creates the same thing as this scenario right here. Okay, so you have charged particles spinning around. That creates a magnetic field. So the Earth has a magnetic field. And here is kind of a look at Earth's magnetic field. It's not pink now, it's kind of this ghostly looking blue here. So this is the Earth's magnetic field. Okay, we call it actually the magnetosphere. It almost sounds like a comic term, DC Comics. Magnetosphere is that protective layer. Now the protection part comes in like this. So you see the sun over here on the left, okay? And the sun is sending all forms of radiation in all directions, including the Earth's direction, which the Earth's atmosphere blocks a lot of that harmful energy. But it's also sending charged particles. So charged particles headed towards the Earth. Our magnetosphere actually is pretty good at deflecting the charged particles and also to a certain extent absorbing the charged particles right here in our magnetosphere. In the magnetosphere, kind of embedded there, they're always referred to as donut-shaped regions, but they're pink on this figure. Can you see those pink regions kind of close to the Earth? So the Earth is very small in here. There's a tiny Earth right there. There's the tiny Earth. Come on, green. Okay, and then right here, let's see what will show up. Okay, those regions right there go all the way around the Earth, and those are actually called the Van Allen radiation belts. So Dr. Van Allen is a local guy in Mount Pleasant, Iowa. Dr. Van Allen is actually taught at the University of Iowa. Yeah, I think he's deceased now, I think. I had a friend who took an intro to astronomy class from Dr. Van Allen. Great guy, I guess, apparently. So, yeah. Slow. So before we leave this subject, there's one more thing to talk about with regard to the Earth's magnetosphere, the Earth's protective magnetic field. Okay, and that is the Northern Lights. Okay, so the Northern Lights actually, it looks like you can kind of see Orion here. Looks like the belt, maybe. I don't know. It's like a weird angle for the sword, but. So the Northern Lights actually occur as the sun has sent an extra dose of charged particles that cannot be accommodated by our magnetosphere. So what happens is those charged particles are going to cascade through Earth's atmosphere at the weak point. And the weak point, that's how I think of it anyway, the weak point is the poles. So basically you get charged particles if the sun is being extra rambunctious, okay, that leak in at the poles and cause these fluorescence to occur. So one of the things, if you've ever heard the poles flipping sort of thing, that's kind of in the news every once in a while. So we have a magnetic field that has a north magnetic pole and a south magnetic pole. Now they don't exactly coincide with our north pole that the Earth rotates on and the south pole that the Earth rotates on, but they're close. So we know by studying rocks that actually our north magnetic pole used to be down here, okay? That used to be our north magnetic pole, and now it's our south magnetic pole. So we know, and actually I can't remember how many times, but it's definitely has flipped. The poles have flipped their relative positions over the course of Earth's history. They know that by studying actually rocks that were frozen at that time and looking at kind of the orientation of the atoms in the rocks. But here's the problem. Remember I said that these are kind of weak spots, okay? To me, and I've heard, and this would be like a science fiction movie, right? So when it's flipping, depending upon how long it takes to flip, we are actually vulnerable at those times to the Earth, to the sun. Now the Earth's spinning on its axis like normal. It's the magnetic poles that are switching. Okay, so there's something to be said for that. Okay, well I think that's a good place to stop. And we'll pick up here on